The design exchange format DEEF file is a crucial component in the electronic design automation EDA flow, serving as a standard ASCII format for representing the physical layout of an integrated circuit. It describes the netlist, placement, routing, and other physical attributes of a chip design. This document outlines the key sections and their significance within a typical DEF file, using an example to illustrate each component. Firstly, I am explaining about file header and design definition section. The DEF file begins with header information including the version, example 5.8, divider char, example /, and bus bit chars, example bus notation, which defines syntax and hierarchy conventions. The design statement names the chip, example top chip, and units distance microns sets the scaling for all coordinates, example 1000 units per micron, indicating nanometer-level precision. The design area, example 00 10,000 10,000, defines the chip's physical boundary. Version 5.8 specifies the DISAF file version. This tells the tool which syntax and features are used. Here, DEF 5.8 standard. Divider char jache defines the character used to separate hierarchy levels in instance names. Example: top U1 means instance U1 inside module top. Bus bit chars specifies characters for bus notation. Example: D0 done for bus signals. Design top_chip declares the name of the design or chip. This design is named top_chip. Units distance microns 1000 sets unit scaling for distances. 1000 means 1 unit equals 0.001 micron, i.e., nanometer level. DI area, example 00 10,000 10,000, defines the rectangular boundary of the chip layout. Bottom left at 00, top right at 10,000 10,000 microns. Second thing I am explaining about rows and components section. The rows section defines the standard cell rows. Example: ROWCORE_1, ROWCORE_2, where placement tools can legally position cells. These rows specify the origin, orientation, and step size for cell placement. This defines 50 rows horizontally and 100 rows vertically. The first site starts at 00. Each site is repeated every 1000 microns in both X and Y directions. Orientation is N, default standard cells placed upright. All rows use the site called core_site from LEF. The component section lists all instantiated standard cells within the design, including their names, cell types, example U1 AND2_X1, and their precise placed coordinates and orientation, example 500-1200N. Instance U1 of cell AND2_X1 placed at 500-1200 with orientation N, north. Instance U2 of inverter cell placed at 5000-2000 with orientation FN, flip north. Third thing I'm explaining about pins and net section. The pins section defines the input-output I/O pins of the chip, specifying their names, example CLK out, the net they connect to, their direction, INPUT output, use SIGNAL clock, and their place. Here we can see pin named CLK connected to net clock, placed at 2200. The nets section details the connectivity of the design, declaring how pins and cell ports are wired together. Example: net clock connects pin CLK and U1/1, while net out connects U2Z and pin out. Fourth thing I am explaining about blockages. The blockages section specifies areas within the die that are restricted for certain operations. Placement blockages define regions where no standard cells can be placed. Example rect 10,000 10,000, 20,000 20,000. Routing blockages prevent routing on specific metal layers within defined rectangular areas. Example layer M1 rect 25,000 25,000, 30,000 30,000. The file concludes with end design. The blockages section defines areas of the chip where placement of cells or routing layers is restricted or forbidden. This is essential for protecting reserved regions, example macros, IP blocks, preventing routing congestion, creating keep-out zones for sensitive areas, aligning with manufacturing constraints. Placement means no standard cells can be placed inside this rectangular area. The lactate defines the bottom left, 10,000, 10,000, and top right, 20,000, 20,000 corners. This could be around macro or reserved analog block. Keep out margin for power structures. Routing means no routing layers can pass through this area. Layer M1 restricts blockage specifically on metal 1, M1. The recti defines the blocked area on that layer. This is often used over macros to prevent shorting with underlying pins, to block critical regions prone to congestion, for design for manufacturing DFM rules. Thank you for watching video. Like and subscribe if this information is useful.